Welcome to this week's colloquium. And today we have Dr. Anna Malanushenko from HAO. And Anya, as I should say, or Annie, received her PhD degree from Montana State University. I guess it's now one of the Montana State mafias. And in 2010, working with Dana Longcope and on twist in the coronal magnetic fields. And then she joined Lockheed Martin Space and Astrophysics Lab as a postdoc, worked with Carol Shriver and Mark DeRosa. And last October, she came here to HAO as an ASP postdoc fellow. So today she's going to tell us what she has done at Lockheed, what she's doing here, and what she's going to do here and then some other place.
Thank you. The objective of this talk is to kind of give you guys an idea of what do I do, what do I know, how can I be useful to you, and how can you be useful to me. I'm going to touch a variety of projects that I've been working on lately. One of these projects, well, actually all of these projects involve the solar corona in this or the other way. Very, very, very beautiful solar corona. And in particular, for example, I have developed a way to use the data that we see, the observed coronal loops, to guide the modeling of the magnetic field. I'm going to tell you how. Here is the idea. So we have an image, just an extreme ultraviolet image, and we see some strands on it that we believe go along with the lines of the magnetic field. But this is just an image, a 2D snapshot. And the idea is to make use of the snapshot to reconstruct the three-dimensional structure of the magnetic field over here. And the way I do it is I trace the field lines by hand. Well, actually, I trace the coronal loops by hand. Then I find some simple model that kind of gives me a pretty good idea of the trajectory in the 3D space and alpha along it. I'm going to talk about it in a second. And that is treated as data. But what I would like to point at this image is that, as time goes by, this active region, or the two active regions, this beast is sitting there without apparently doing much. Or at least some of the coronal loops appear, some of the coronal loops disappear, but kind of the overall geometry is more or less the same. So my modeling would include, would assume that the magnetic field is in equilibrium. But first, how do I transform the 2D data into the 3D data? Oh, yeah, I said that already. So let's take one step at a time. Suppose that we see a coronal loop, showed yellow here on this image, and suppose for a moment that we knew what the magnetic field is. Suppose that we had the data cube. In that case, finding the field line that matches this coronal loop is pretty easy. What you do, you pick a point on the coronal loop, let's say a midpoint, and you trace many field lines in the data cube along the line of sight, and then you project them into the plane of sky, and you figure out which of the field lines matches the coronal loop the best. And that will be probably the magnetic field line that was involved in the creation of this coronal loop. But then the next thing, of course, we do not know, in general, the magnetic field. So what to do? Well, the same thing, actually. So for a given loop, just try many simple fields. And by simple, I mean constant alpha fields. And try and find the best matching field line in each of those constant alpha fields, and then find the best of the best. What is the constant alpha field? As I said, I'm talking about the equilibrium fields here. By equilibrium, I mean force-free fields. And by force-free field, I mean in the low beta solar corona, the plasma density is so small that the plasma pressure, the gravity are very small compared to Lorentz force. So when people talk about coronal equilibrium, the equation to write is that the Lorentz force at every point should be equal to 0. And I just rewrote this equation. J cross B is equal to 0. And this, of course, means that J is parallel to B, where J is the magnetic current and B is the magnetic field, which means that there is a scalar constant of proportionality between them, alpha. So J is equal to some scalar alpha times B. And of course, J in its own turn is curl of B. So this is the equation. And a constant alpha field means that alpha is constant everywhere in the computational domain. The way I presented it here is just a mathematical abstraction, but it actually has a geometrical meaning. Alpha, just to give you an intuitive insight, here are several constant alpha fields. For alpha equals 0, also known as potential field, alpha greater than 0 is less than 0. And you can see how alpha is related to how twisted and how sheared magnetic field lines are. And that has been actually shown to give us a pretty accurate idea of what the twist in the non-constant alpha fields is. Let me show you an example. Actually, I like this image from Burnett et al. 2004 because it shows two things. One thing is that it overlays two constant alpha fields over the same active region, and you can see that each of the fields is pretty good at modeling northern or southern half of the active region, and B, a single constant alpha field is not good for modeling the entire structure of the active region. So the more general case is nonlinear force-free fields, or non-constant alpha force-free fields. So I'm just going to derive some equations. Well, we can take this governing equation, take the divergence of it, and make use of the fact that there are no magnetic charges, and come up to this equation. This equation basically means that alpha has to be constant along the magnetic field. So for a given magnetic field line, no matter what field, if it's a force-free field, alpha has to be constant along every individual field line. But of course, alpha can vary across the field lines. Well, the second equation, just for illustrative purposes, we can take curl of this equation again and do some math and come up with this equation. So this is a vector equation. And you can see that different components of B are entangled with different other components of B. And in general, this equation is nonlinear. Vector equation is 3 scalar equations, and this is a scalar equation. So we have a system of 4 equations, 4 unknowns, the 3 components of B and alpha. And this can be solved as a boundary value problem. And the boundary conditions are the following. The magnetic field, the normal component of the magnetic field on the boundary of the domain, plus alpha on every field line. How can we know the latter? Well, we can know it from vector magnetograms. Right, just using the fact that alpha is a proportionality constant between J and B, you know, if we know By, Bx, and Bz at the plane, we can figure out the distribution of alpha at the boundary. Well, and then wonderful, we have a data cube. We have the line of sight magnetogram as the B boundary condition, and then we have vector magnetograms as the boundary condition for alpha. And then we solve it. Well, easy, right? Well, no, not easy. There are many problems when solving this equation. And I'm just going to show you one of them. This is what this problem is. Or if you draw it to scale, it's going to be more like this. But the idea is that this is the transition region. And the point I would like to make here is the vector magnetograms are measured at the photospheric level, where we cannot neglect the pressure force, we cannot neglect the gravity force because the plasma is dense. And it means that even in equilibrium, this equation is not true. It means that this equation is not true. So just putting it in other words, we measure alpha over here. We try to find a solution above this region, but alpha does change along the field lines between this point and, say, that point. So this is a big problem. There are ways to to somehow find a solution to fix for it. But I tried to bypass this problem altogether. We have a pretty good idea of what the normal component of the magnetic field is. But I tried to figure out how to measure alpha in where it belongs, in the stratified force-free corona, right over here. But then it would not be a boundary value problem, right? It would be a problem with some sort of constraints in the volume. And this is what I've been working on at Lockheed Martin. And we came up with a way of solving this problem subject to those constraints in the volume, alphas along the 3D trajectories of the magnetic field lines. And the method we came up with is called QuasiReuben, which is derived by a modification of a well-known Grad-Rubin method. And I'm just going to quickly mention what it is. So in a Grad-Rubin method, you start with some initial guess for the magnetic field, potential field, for example, as the case might be. If you know the normal component, there is a unique potential field, right? Then the Grad-Rubin method uses vector magnetograms, and it says, hey, we know that alpha has to be constant along every field line. So we can build a 3D cube of alpha by just, tracing a field line from every point in the domain, looking at where it lands at the lower boundary, and assigning the alpha with accordance to where it ends. And so basically propagate alpha along the field lines of the first iteration of the field. And then we have the volume filling cube of alpha, but then curl of B0, of course, is not equal to B0 alpha 0. So we can uncurl this equation and get B1, the first iteration, from which we can do exactly this step and propagate alpha along the field lines of the new field and get the new iteration of alpha, and so on and so forth. To my knowledge, this is actually the only force-free method that has been analytically proven to converge for small alphas and for well-posed boundary conditions. So the quasi-Grad-Rubin is what we made it. Phil?
Just naively, I would have thought that alpha of 0 is 0.
In the volume, yes. On the boundary, no. So alpha of B0 is 0. But here's an idea. We know what alpha should be in the volume. It should be A constant along the field lines of B, and B, it should match the boundary value alpha. I mean, of course, alpha that you can get this way would be inconsistent with B0. And this is the point. This is why B1 would not be equal to B0. But if you do it on and on and on, the iteration will eventually converge.
Okay, so how do you get the starting value of alpha that's not 0?
You get it in the boundary. So here's how. Let me put my coffee mug away for a moment.
You have a current along the field line. All you have to do is have a current along the field line without alpha being 0.
So here's the thing. So you have a data cube. And you know alpha over here. So what you construct is not consistent with the existing field. But what you do, you pick a point, you trace a field line, you see where it ends, you evaluate alpha over here, and you assign this value to the alpha at this point. Does this help?
So in solving your differential equation, it's a second order equation. You need a couple boundary conditions. You have the radial field at the surface. Normally for potential field, you have an outer boundary condition that the field goes away at infinity or becomes radial. Mm-hmm. So does alpha replace that other boundary condition?
This is one of the other problems in solving the system. Usually people assume that either field lines are not allowed to escape the domain through side or top boundaries. Another way of doing it is imposing periodic boundaries. Then yet another way of doing it is saying, well, whatever field line leaves the domain through the top or through the sides has to have alpha of 0, meaning it has to carry no current. But yeah, I mean, if we had the measurements of alpha and of B on the side boundaries, the problem would be easier.
Just for clarification, so if I understand, you have alpha at the boundary from, I guess, the curl of the first field, but you actually have two values of alpha, right? If both field by then, which one do you choose?
This is the third problem in solving the nonlinear force-free field equations. And this is a bigger problem than you might think at first sight. So here's why. So suppose that we have two polarities, plus and minus, okay? And we have some distribution of alpha over here, and we have some distribution of alpha over here. if alpha has to be constant along the field lines, then suppose we pick all the points that have a certain value of alpha, I don't know, 0.1, whatever, and calculate the magnetic flux that encircles this region. The corresponding region in the positive polarity, whatever it is, it has to carry exactly the same amount of flux. Given that the measurements are not perfect, there are always errors, there's always noise in the measurements. This is in general not true. So one way of dealing with it is just to take alpha from the positive polarity, or just from the negative polarity, or try to blend the two, or find a solution for one, then find a solution for the other, mix them, and then find a solution for one again, and find a solution for the other again, and mix them again. As I said, this is a big problem, both analytical and practical. And this is one of the motivations of why I tried to do what I did, and QuasiReuben. So the only thing different is, instead of propagating alpha towards the foot point, one or the other foot point, instead I have some initial guess of alpha, and what I do, I trace the field line in B0, and I average alpha along the line of B0. As an initial guess, as I said, there is a way to come up with the well, to reconstruct the coronal loops, or to reconstruct the magnetic field lines that correspond to coronal loops. The output of this procedure is 3D trajectories in the volume that have certain alpha on them. So the initial guess could be something like Voronoi cells that use these trajectories as skeleton. And then on each iteration, the alpha along the trajectories is reimposed again. And the rest of the iteration is the same. The field is uncurled. We get the new iteration of field. We average alpha from the previous iteration. We reimpose the constraints in the volume, and so on and so forth. Well, to be fair, there is a fine font here. Well, there's a fine font in many numerical procedures. And the thing is that when I reconstruct the magnetic field lines from the coronal loop images, I underestimate alpha. And I knew this ahead of time. I also know that this underestimation is linear. So here I'm showing you a nonlinear force-free field, and then with some field lines that I projected into this into the XY plane. I pretended they are loops. I fit them, and those are the results of the fit. And those are the actual alpha versus the alpha that resulted from the fit. The underestimation is linear, but the slope of the line is slightly different in every case. So in reality, what I get is alpha prime, which is some constant f times alpha. I don't know currently how to calculate it, but that's not a problem. I can evaluate it. Here is how. I can make this iteration, but instead of alphas that I found, plug in some, use some multiplier. So solve for the magnetic field with the same constraints in the volume, except that their magnitude is different by a scaling factor. And I can try various scaling factors, and I can find the one that matches the loops the best, the observed geometry again. So there are like two iterations. There's an iteration within an iteration. And to illustrate on the same very example that I just showed you, on this plot, I plotted the quality of fit as a function of this imposed scaling factor. And 0 means perfect match. And you can see that as my multiplier, every parameter goes from 1 to 2.5, we get a better match, and then worse match progressively. And the minimum was achieved at the f value of 169. And this is the same plot that I just showed you earlier, alpha that I found from the 3D, from the EUV image, versus alpha that corresponds to the actual field. And I overplotted the line of the slope of 1.69, and well, I don't know whether this is surprising or not, but you know, the slope is pretty much exactly the slope, the underestimation factor slope. So this is to say that, yeah, there is this constant factor. I cannot calculate it ahead of time, but I can evaluate it. Yeah, this is the question, right? Does it work? Well, it does work. There are two papers I can refer to. And there are multiple tests there. I'm just going to show one of those tests. So I took a nonlinear force-free field simulated by someone else, and just for bookkeeping, it's a Whittle ++ field from Shriver et al. 2008, but it doesn't really matter. This is my correct answer. This is my synthetic corona. So I traced magnetic field lines over here, and I projected them into the XY plane, and I ended up with the 2D trajectories. And then I said, well, can I reconstruct the correct answer using just those 2D trajectories and the normal component of the B at the photosphere? And so this is the data plus the line of sight magnetogram. These are the potential field lines for comparison. This is the correct answer, and this is the solution. And the field lines of this solution definitely match the correct answer, or quantitatively, they match the correct answer better than lines of the potential field. And this was one of the points of the null simulations paper in 2009, of the Rosa 2009. They said that, well, how about we try to model this active region? And they gave people the active region, and they've concluded that no models come up with a better match to the observed loops than the potential field. Well, in the case of this solution, this is clearly not the case. The shape of the field lines matches the correct answer much better than potential field. And Sarah?
Do you have a quantitative chi-square type measurement of that, or do you have?
I sure do. It is actually over here. It is actually this value.
Are you doing a point by point across the field of the simulation?
No, actually, what I do, I have loops which are the 2D trucks. I can find the best matching field lines in the solution, and I can compute the average distance. And I can do this for the potential field and for the solution, and quantitatively compare the numbers. But you can kind of guess where this curve will end as I will go closer to 0, right? So this is the average distance. So yeah, there's this quantitative measure, and I report the numbers in the paper. Here, I would much rather show some pretty pictures. Say this is the distribution of the current, vertically integrated for the correct answer and in the solution. You can see that the large scale features are reproduced pretty well, but the fine scale structure is gone. But this is expected because the code is diffusive in nature, diffuses alpha across the field lines. It has to come up with a smooth solution. But the point is that the large scale features are there, and this is current. And here I would like to point that I'm not using vector magnetograms, right? They're not the input, but they are the output, because the end solution is the data cube of the magnetic field vector everywhere, including at the lower boundary. Well, what does it look like at the lower boundary? Does it actually reproduce the vector magnetogram at the lower boundary of this model field? Well, see for yourself. Here I'm showing you the Bx and By for the reference field, and just to make my task tougher, I subtracted the potential field. The field is weakly twisted, so the major contribution is the potential field. So I subtracted that. So Bx minus Px, By minus Py, and Bz minus Pz is 0, right? So this is the correct answer. This is the solution plotted on the same grayscale. I'm going to flicker them back and forth. And those are just scatter plots point by point. As you can see, they're very well correlated. Although the fine structure is gone, but the large scale features are there. I have tested it on the actual vector magnetograms in actual solar data. As I said, this is so this is the model of the field in the corona, right? So the lower boundary, in principle, corresponds to the lower boundary of the corona, which is not the same as the lower boundary of the photosphere. I'm sorry, which is not the same as photosphere, and the magnetic fields are not necessarily the same. But yet, I have reconstructed a field for an actual active region. I have compared it to the vector magnetograms for the same active region. The values were correlated, but they were not the same. And one of the things I would like to know is how well does it reproduce the actual magnetograms in the lower boundary of the corona. Maybe by using some simulations, maybe by using some observations, I don't know. But this is what I would really like to know. So the actual solar data. Here's an example. This is just the 171 image of the active region that is the most studied active region in the current solar cycle. There are over 30 papers in ADS devoted to this active region. The Valentine Day flare event is the most notable event. So anyway, those are the loop tracks that I just drew by hand over the coronal loops. And those are the constant alpha fits to those loop tracks. So those are the 3D trajectories with alphas on them. So those are the inputs to the simulation. And this is described in the paper that I'm advertising here. Those are the field lines of the solution. And in the 2014 paper, we argue that the solution is very, very force-free. We come up with a variety of metrics. And we also try to plug it into different MHD codes, for example, in Duhong's MHD code. And what we saw is just slow numeric diffusion, nothing else. So this is indeed a stable equilibrium state. Key features. I have a way to reconstruct the coronal magnetic field that A, matches the loops, B, matches the loops by design, C, it's very, very force-free, D, of course, at different times you see different loops. So I picked a time when this active region was just sitting on the disk without doing much over a scale of several hours, and the loop lifetime is 20 minutes. So I just tried to do the natural bootstrapping. I presume that the field didn't change much over, let's say, 1 hour. I did several reconstructions 20 minutes apart from different loops, and I have verified that indeed the field, the resulting answer did not depend much on the selection of loops. And I found that this is also the case for the situation right after the magnetic field, right after this active region has flared. I also found that the solution is more sensitive to the selection of loops right before it's about to flare, which is interesting on its own. Imagine that you're tracking an active region, making models, and as soon as your models start to break, you know that something is about to happen. But even despite the sensitivity, we were able to evaluate the energy release in this X-class flare. And here's this plot more clearly. So here the dotted line is potential field energy over the time. The gray bar is the time of the X-class flare. The solid line is the total energy of total magnetic energy of the field. So their difference is the top limit to how much energy can be released in the eruption. And the lower curve is actually the metric of how force-free is the field, 0 being ideally force-free, and it cannot exceed 1 by the way it was constructed. So you can see that right before the flare, the field becomes progressively less and less force-free, but it still stays, it still stays, let's say, closer to 0 than to 1. And for one of those models, we have verified that it is stable in the MHD simulations. So those are the stable equilibria. Regarding this point, in the paper, I argue that this is a boundary artifact. But even if you do not treat it as such, I mean, even if you were the devil's advocate, you would say, well, how about we just average these 3 points right before the flare and these 3 points right after the flare? There would still be a very conservative, but the energy drop estimate would actually be of the order of 10 to the 32 ergs, which is a pretty good estimation for X2 flare. And it's actually an underestimate because, as I said, I used the line-of-sight magnetograms, which means that in the region of strong field, there is a saturation effect. So I underestimate the field in the regions of the strong field. The actual field is about 1.2 of what is measured in the line-of-sight fields. And you can actually verify it by, there are 2 papers that there are two papers that mention the potential field energy for this active region, and potential field energy is, I mean, potential field is unique for a given magnetogram, right? So the two independent observers should come with the same answer for the energy of the potential field, but their energy is actually, the energy in two papers is actually different by a factor of 1.6, and one paper uses line-of-sight magnetograms, the other paper uses vector magnetograms. And this comes very well in lines with that, the energy is just the integral of B squared. And if B is stronger by a factor of 1.2, you ought to come up with an energy of 1.6 bigger. So the estimate that I have is probably, the actual drop of the energy is probably 1.6 bigger than that. So this is a very, very, very conservative estimate. Sarah?
You mentioned that might be an artifact, but the point gets to a peak, and it seems to be dropping before the flare. Is that real or significant?
I don't know, but I know that I know that the solutions become more noisy if you do them if you do them in a sequence. I know that the solution become. I mean, if you compare the solutions, the sequential solutions, they differ more and more right before it was about to erupt. So I don't know whether this is noise or whether this is actual, but I'm going to say that this is maybe within the limits of the noise. But this is the only estimation of noise that I have. And the estimation of the noise in the quiet phase of this active region is much, much smaller than that. And in the post-flare phase is also smaller.
So when you say you're approaching the flare, during that time, what is actually changing in affecting your model? For example, the photosphere probably hasn't changed very much.
Correct.
So your boundary, so what is changing when you do this sequence of models as you approach the flare? Is it the coronal loop starting to look different? That's what's changing the model.
Well, if we were to say that, let's say the coronal field did not change much, but different loops lived at different times, I'm going to say that even if they were like different sets of loops drawn from the same field, the solutions were slightly different, well, or a lot different in this case, and slightly different in the quiet phases. So it's the set of loops that is changing.
So that's what's changing most.
Well, it's hard to believe that the energy of the field has increased by this much over the scale of 10 minutes. Those 2 points are 10 minutes apart. All right, so it ought to be the artifact, but I don't know.
The right axis, the one on that side.
It's the force freeness matrix for this plot.
So it's J cross B divided by something, J dot.
No. You see, if you calculate J cross B divided by J dot B, well, if in the regions where J is 0, you will kind of be dividing 0 by 0. And if you do math, you can actually show that statistically you will come up with 1. This is why I didn't use this. Okay, I reported this metric in the paper, but I came up with the metric that is not sensitive to the lack of currents. It's basically the magnitude of Lorentz force divided by the magnitudes of the two components of the Lorentz force, the magnetic pressure and magnetic tension. And it's nicely normalized to be between 0 and 1, and it's 0 when Lorentz forces are 0. Another feature of this simulation, I'm going to show you two images of the two solutions before and after the flare. So this is a close-up at the core of the polarity inversion line. Don't know if you can see on the screen, but there is a bundle of twisted loops over here, over the polarity inversion line, which is kind of similar in shape with the 304 angstrom image. And this bundle changes the shape dramatically after the flare, which is also in lines with the 304 image. And the 304 image was not used, so it's an independent validation. Over here, I just take a cross of the over this plane. So what I show here is the total current on field lines. So you can see that I'm not going to say flux rope, I'm not going to say filament, but I'm just going to say a bundle of field lines that carry a lot of current on them, and that carry a lot of twist on them. Here I'm showing the isolines of twist, and in the core, the twist, in the core, this bundle becomes pretty close to making one full turn along the axis, this bundle is gone after the flare. And we have already verified that this bundle is stable, is in stable equilibrium. So one of the things I would like to do is to figure out what kind of disturbances would make this bundle go unstable. Is it the photospheric driving, or is it some sort of the coronal disturbances, such as coronal waves, for example, or maybe some sympathetic eruptions, or maybe some changes when some distant changes in the overlying field make this particular structure unstable. Well, but anyway, this is one of my this is questions of my immediate interest. But there's more than one thing that can be done with this kind of data cubes, and I'm going to talk about some other things that I've done with it already. And one of them is studying of the coronal heating. Well, you see, we have beautiful images of the solar corona, and we have the magnetic field model that matches the coronal features by design. So what we can do, we can model the coronal emission and just compare feature by feature, pretty literally. I mean, forward models. And by forward model, I mean, well, there are many models, physical models of how the corona is heated. So pick one, applied to the model of the corona, forward model the emission, and compare the result to the observations. This is the idea. There is more than one approach to it. In particular, there is 3D full MHD simulations, which are pretty costly, but are probably more precise. The second approach is to slice the entire magnetic domain into many small, thin flux tubes and model each one of them separately as a 1D structure. The reason now behind it is that plasma well, since plasma is frozen in, so let's consider this flux tube, and let's say that this a heating event has happened, and let's consider a flux tube that is embedded in this heating event. The plasma is a very good conductor along the magnetic field, and is a very bad conductor across the magnetic field. So the temperature will get so the temperature will get conducted along this flux tube, and the plasma will get conducted along this flux tube. It pretty much won't interfere with its neighbors, at least in the low beta situation. So this is the approach that I take also. And I use an existing 1D model that allows for quasi-steady solutions. So it allows for subsonic flows, and it allows for variable cross-section, arbitrary geometry. I can specify the volumetric heating arbitrarily along the loops, and well, then I can take a heating model. I can use the same heating model for many small flux tubes drawn from this field and synthesize the rest. Synthesize the emission. I would like to mention that something very interesting showed up when I started doing this. My computer reminds me that I need to turn on IDL. Here's the thing. So let's look at the magnetic bundles drawn from this very field. So what I did here, I drew circles in the positive polarity, very small circles, and I initiated field lines from these circles. And I considered, and I filled the volume between those field lines. I just treated it as a small flux tube. So those are the renderings of those little flux tubes. As I said, their foot points are circles. But look at their shape closer to the apices. They're not circles. They're more like ribbons. And to give you a better idea, so I'm going to show you just the apices. So I'm going to show you another field, just because I had an illustration in my pocket, but it would be a field in which I traced many field lines from hexagonal grid, and I'm going to show you the apices only. So this is the data cube. It's filled with potential field. It has positive polarity. It has negative polarity. The negative polarity I split into many hexagons. They're nice because they are somewhat close to circles, and they fill the entire what is the English terminology? They're filling the entire 2D plane. So I initiated field lines from the corners of those hexagons, and I looked at those flux tubes defined by those hexagons at their apices. This is what they look like. The foot points of those flux tubes are regular hexagons, and this is what their apices look like. Now, how many regular hexagons do you see here? Well, some. Maybe 1,000 out of 10,000, to do some statistics. And I did indeed do some statistics. Let me show you. So I compared. So I looked at them. So I said, well, if the apex is an ellipse of some sort, what is the squashiness of this ellipse, or what is the ratio of the two semi-axes of the ellipse? And this is the histogram. The peak is at about 2, but there are ellipses that are squashed by much more than 2. In fact, most of them are squashed by much more than 2. And then, of course, if I look at the expansion, assuming that the loops were circular in cross-section, I would get, let's say, this value for expansion. I cannot see it. It's like 1 point something, 1.5. And then if I look at the expansion separately for the two axes of the actual flux tubes, I would see that those two numbers are very, very different. And these histograms essentially show that the vast majority of the flux tubes expand in one direction, mostly, and not in the other direction. So they flatten up, they become ribbons. Why do we care? Well, there are many reasons. This is actually a very impactful finding. For example, this feature of the magnetic field, and I'm going to argue that this is the intrinsic feature of the magnetic field, is going to affect how we perceive the loop's expansion. Here's a rendering of some magnetic flux tubes. This is just an isothermal situation, and all of those flux tubes have the same scale height. And I'm just rendering the density squared. And all of them have the same size at the foot point. Look at the small part of this image. Well, you can see here several bright and crisp and thin loops that do not expand much. And you cannot see, well, maybe over here, and I can see more on my screen, there are also loops that are diffuse, but they are very dim. What's happening here? One of the things that's happening is, suppose that you're looking from this direction, okay? Now, if you look from this direction, and if the two flux tubes, let's say this flux tube and that flux tube, are lit in the same amount, then the column depth of this flux tube would be big for the observer that's looking from this direction, and this flux tube will appear very bright but very thin. And the same flux tube oriented differently will appear white but very diffuse. Now, of course, suppose I didn't tell you all that. Suppose that you just want to study the loop expansion based on this image. Which of the loops would you choose for the analysis? Well, obviously those that are better visible. So it imposes a bias. And this is to address the problem, and this is a well-known problem, that coronal loops do not expand as much as we believe magnetic flux tubes should. And this is to point that we should be very, very, very well aware of this bias in order to measure anything like that. Charlie? Okay. The other thing that why we should care about it is because it affects observed pressure scale height. Here's what I mean by that. Suppose that the atmosphere is in equilibrium. And let's say it's an isothermal equilibrium. So if we consider a small column of plasma, then the density, a small vertical column of plasma, the density is going to drop exponentially with height, right? So if we project, if we look at the emission of this small column, the emission is going to be proportional to column depth at each point times the density squared. And the density is going to drop exponentially. So if the column depth is constant, then we can get the scaling law that the emission measure should scale as n squared as a function of height. But then, of course, magnetic field strength drops with height. So magnetic flux tubes expand with height. And the traditional view on that is that they expand with height isotropically. And I'm saying traditional, but this is also the simplest view, right? I mean, if we don't know anything else, we might as well just assume that they're circular. And in that case, we can say, well, the flux along the flux tube has to be conserved. And the flux is proportional to the magnetic field strength times the area. And the area is proportional to radius squared. So the column depth, you can say that the column depth is proportional to 1 over square root of b. And then the scaling law would be density squared times 1 over square root of b. And the problem is that there are multiple observations that show that show evidence of this scaling law rather than the scaling law. And this is another big mystery about the coronal loops. And there are many proposed solutions. One of them is, for example, Craig de Forest solution. And he said, well, suppose the loops are just very thin. They're much, much smaller than the resolution of our instrument. Then you can do the same sort of math. You can work out the filling factor, the column depth, and you can get out this scaling law, which actually is closer to the observations than the naive scaling law. This is a very beautiful and very, very simple theory, and it also has serious consequences. For example, it says, well, if the loops are unresolved at the apices, it means that we can put an upper bound to their width because we know the resolution of our instruments, right? And since we know how much the magnetic field should expand, we can put the lower bound to the foot points of the loops. And this is very, very important for studies of coronal heating, because it means that whatever heating events, should they happen at the foot points of the loops, we know their spatial extent. We can constrain it. Now, I'm going to say, no, we cannot constrain it. I'm sorry, but suppose that we have the same loop viewed from two different sides. In one case, it expands along across the line of sight. In the other case, it expands along the line of sight. The perceived drops of density with height, the perceived drops of intensity with height are going to be very different. And we will probably find out that this loop is overdense and this loop is underdense. And we will also find that this loop does not expand too much. Yeah, it makes it harder to put an upper bound on the size of foot points. And I'm just going to make a point that we should be very, very well aware of the anisotropy of expansion if we were to put any spatial bounds to the sizes of coronal loops. Well, someone can say, well, let's build better instruments. Well, I'm going to say no. It's not going to help. Okay, so I did say that if you have a loop this wide, its foot point might be this big, or it might be an ensemble of loops whose foot points are very, very small, and we cannot distinguish the two. Here's an example. Suppose that the loop has this type of cross section. On our CCD, we will see a bumpy profile, and we might be convinced that this is a bundle of loops that are produced by a series of independent heating events, while in fact it could be the same heating event. Or if I take the analogy further, well, maybe this will be too much, but I'm just trying to make the point. Well, what if what we see are just ripples on the whale curtain? In that case, as the resolution of our instrument increases, we are going to see finer and finer and finer structure, but it doesn't mean that we're going to resolve finer and finer events. It might be the same event. So I think this is very interesting, and I think we should be very well aware of this anisotropy. It has a lot of consequences. Well, the consequences for me were that I just constructed the flux tubes with the actual cross section, and I just modeled the density and temperature along them, and then I just rendered I just rendered them using the actual cross-section that I found from the magnetic field. Yeah, and the heating models. There are many proposed physical mechanisms of how the corona is heated, and this is one of the attempts to organize those models. And if you organize it, you can see that one of the things different between the models are, and all of them. So this table shows the volumetric heating in many of the models. Let's say that if the loops are heated with resonant absorption, then the volumetric heating should be this, or if they're heated by current sheets, then the volumetric heating should be that. And they're very different in the first case in the powers of the magnetic field strength along the flux tube, and the length of the flux tube. So most of those heating models propose that the volumetric heating is proportional to B to some power times L to some power. I just plotted them on the power of B versus power of L plot. And what I did, I just explored all of those heating models. So I plugged each heating model into the entire ensemble of the small flux tubes, and I rendered all of them together, and I got a synthetic EUV image. Well, these red crosses were not enough, so I've expanded my parameter space a little bit. And here, I would like to point out something. So there are more parameters. For example, the total heat input into the active region. This is something that we think we can constrain from other means. Or, for example, there is a total heat that enters each individual flux tube that some people argue should also scale as the power of B at the base and the power of L. And then there might be some tapering function F that incorporates all of this column, which can be density or velocity or other parameters. Well, I guess I'm about to formulate the principal law of the free parameters. Free parameters multiply. There are more and more of them. And unfortunately, we cannot simplify the problem. A lot of simplifications that appear reasonable at first sight, if you do a math, it will be a very heavy, a very bulky math, very, very inconvenient. But you can show that simplifications constrain some of those parameters tacitly. For example, the zeroth approximation, let's say loops have constant cross-section. And then you might think that you're exploring this parameter space, but in fact, you just constrained your power of B to be 1, no matter what. And if you plug in other powers of B, then the solution will be simply inconsistent with the model. Or, for example, another pretty reasonable assumption is to use average field strength along the loop. And to say, well, it's a characteristic field strength. It's going to be different for different loops. And it's going to be some sort of a characteristic field strength. As soon as you do that, you constrain the power of B to be 0. Another thing is that, for example, you can say, well, we can parameterize the volumetric heating as some function of distance along the loop. Well, as soon as you've done that, you've tacitly related two other parameters, the power of L in the volumetric heating and the power of L in the total heat that enters the base. If, for example, the volumetric heating depends on density, as the case might be in some models, well, the models predict that it has a very weak dependence on density, but nonetheless, if it depends on density, then this power and this power are not directly related or not linearly related, or, I mean, I couldn't relate them at all unless I made some other simplifications. Another example, well, constant heat influx, well, it makes sense, right? I just told you that a plasma is a very good conductor along the field and a very bad conductor across the field, right? So one can say, well, the heat influx, well, you know, it should be conserved along the flux tube, because where else can it go? Well, as soon as you've done that, you constrained your power of B in the volumetric heating again. So I'm just trying to, again, make people aware of this. There are many other simplifications. I also made some simplifications in my modeling. In particular, I made this simplification that relates those two powers. But I'm aware of this, and I'm making you aware of that too. So we've done that. And I beg your pardon, the free parameters, they multiply, right? So I have the power of B, I have the power of L, I have these two powers that I cannot directly, in general, relate to those two powers, and so on and so forth. So I have 1, 2, 3, 4 different parameters and, several thousand simulations in 6 synthetic AA channels. So I've got several thousand images. An example of 2 images. I'm not saying that those are the best images. I'm just showing you how different can there be. And is it humanly possible to go through these tens of thousands of images and compare something somehow? Well, not to say I didn't try, but there has to be some quantitative measure. And here I'm going to take an advantage of the fact that the model matches the observed coronal field by design. So I can just take this field and, as I promised, do literal feature-by-feature comparison. So I can integrate the intensity in the core, in the periphery, in the more distant periphery, and so on and so forth, in the observations and in the simulations. And I can do it in many I can do it in many wavelengths. And I can come up with a cloud of points. Here, different colors correspond to different wavelengths, and different letters correspond to the different regions. And this is nice. This cloud of points is very nice because once you have this, you can characterize the model by chi-squared. And lower chi-squared is better fit. And I don't believe I've looped this image, actually. So you can see that some of the proposed heating models result in a cloud. I mean, the intensity is not correlated with observations, and some are better correlated with observations, and so on and so forth. And then I can minimize the chi-squared and find the best of the best. Well, I'm not going to show you the best of the best for several reasons, but I'm close to making conclusions in this project. Well, one thing is that, so this is the parameter space I showed you, subject to some other free parameters as well. So for this selection of other free parameters, this is what the chi-square looks like. And red means higher chi-square, white means lower chi-square. And you can see that most of those red crosses, which are the proposed theoretical models of how corona is heated, most of them lie in the red regions, I mean with high chi-squared. So it means that most of the heating mechanisms can be ruled out. The other thing is that, as I showed you earlier, well, some of the images are generally successful. The problem is that I could not find a single model that would model both the core and the periphery equally well. That means that maybe I need to go beyond the simplifications that are already made. Maybe I need to go beyond the quasi-steady equilibrium. Or, well, maybe new heating mechanisms or new theoretical models are needed. And should they appear, we have constraints for them. And I will stop here. Thank you very much.
Questions?
So that cloud was really interesting. So what you were plotting there, was it observations versus models then? And so essentially, the more it follows the diagonal, the closer it is. And what you ultimately want is that all the colors to be along that line, because that means all the wavelengths agree, and all the letters, because that means all the regions agree. Okay, so your chi-squared is somehow measuring how close everything is to that line? Mm-hmm. Okay, so, and you're saying you can't really get one thing that works for the core and for the diffuse. Mm-hmm. So if you were to, is it possible you could have two different mechanisms for those two regions and solve for that by reducing the numbers of letters you're putting into that fit?
This would be a direction. This would be one of the directions for future studies. I mean, this would be my thought. But then again, there is this Occam with his razor that says, well, don't use two hidden mechanisms if you can come up with one. But over here, I can't really come up with one. But I would like to know what it is. And maybe so what you just said is one way of doing it. The other way of doing it is to take MHD simulations of the corona, such as Matthias's simulations, and examine them. Look at their heating, try to relate it to those parameters that I have, look at how quasi-steady it is, and try to figure which of those theoretical models, if any, to produce the best.
So can you relate the free energy in a loop to the current helicity in the photosphere? If you're basically assuming you're getting your alpha from saying Jz is equal to alpha Bz.
Mm-hmm.
So the current helicity is Bz times Jz, so it's alpha B squared. And does that uniquely determine what, because if alpha is 0, it's a potential field. So does basically the value of alpha mapping on the photosphere and the value of the magnetic energy, vertical magnetic energy in the photosphere, does that uniquely determine what the magnetic energy is in the loop above the potential?
This hasn't been proven in general. Basically, I'm just rephrasing your question. Given the distribution of alpha in the lower boundary and B, is the solution unique? The uniqueness of the solution has not been proven in general, to my knowledge, but for the QuasiReuben mechanism, it has been proven to converge in the limit of alpha going to 0. This is about as close to the answer as I can get.
I was just wondering if you can take your different models and plot the magnetic energy that you get in the loops versus the current helicity in the photosphere. If there is a relation there, then you can have a shortcut to estimating the magnetic energy in loops by just using the photospheric observations of the current helicity.
In individual loops, yes, but what about the entire volume? And the free energy, you initially said free energy. It's very hard to define free energy in a subvolume. I mean, free energy is a function of both the field and the shape of the boundary, right? So while there is such a thing as, say, energy density, I'm going to argue that there is no such thing as a free energy density, for example.
I have a question regarding this coronal heating problem. The way I understand it, the only way you can distinguish between different heating mechanisms is kind of, you have to make the assumption that actually the microphysics determines the amount of energy which is dissipated. And are we sure that the corona is operating in this regime? And this is very opposite to what we expect, for example, for turbulence. There actually the macrophysics determines the energy which is dissipated. The microphysics only determines the scale where this happens.
Actually, turbulence is one of the models in this table. If you do some math, you can figure out how does the turbulence map into this power of L versus power of B scaling laws on the micro level. Does this answer your question?
I mean, it just sometimes it's strange to me that when the details of the microphysics determine the amount of energy which is dissipated, and that is normally set up by more macrophysics, which determine how much free energy is there you can dissipate.
Well, think of it this way. We take some macrophysical, well, in particular for turbulence, we take some macrophysical parameters, and we figure out how exactly they're going to involve, how exactly they're going to affect the heating at this particular point or at that particular point. So to say, they can be used to figure out the volumetric heating everywhere in the domain of the macroscopic scales. And then the result would be subject to this very modeling.
So just a comment on a question. Actually, two questions. The models you solved for in your first part of your talk are continuous solutions, right?
Define continuous.
Differentiable.
Mm.
That's the field lines.
Sure.
Okay. So even so, you get that argument, and it's amazing to me. I mean, that's a property of a potential field that you're showing with the squashing of the hexagons. That's nothing to do with currents or anything. I mean, it's just so sheet-like or going away from a tube-like picture seems to be something that important. And, I've been arguing this for a long time in the chromosphere, so I kind of like the way you're going there. But aside from that, the question is, related to what Matthias was just saying, why would you ever adopt B and L as your fundamental parameters? Just because you can observe them. I mean, what you actually have going on is you have an injection of electromagnetic energy at the base, balanced by something. You got to balance that injection of energy with some dissipation at the top. So I would like to see a pointing flux, and then inject it at the base, and then you just look at the balance between that and everything else. And people make arguments that B and L are related to these things, but imagine that in the photosphere you've got small scale reconnections, current sheets being set up. The injection of electromagnetic energy is not even observable on the scales you're looking at. So I'm just astonished that I'm not surprised at all that you get something very non-unique, but also kind of almost not nonsensical, but something puzzling about doing this, because I don't think you should ever use B and L here.
Or B at the base. Well, L, at least in some of the models, L is some sort of a, you're going to laugh, but it's some sort of a proxy for the angle between the nearby field lines, so it's like a measure of alpha, if that makes any sense at all.
Well,
I think this is Parker models.
I think of the simple observation that the cores of very strong active regions in sunspots have almost no coronal emission. Those are unbelievably strong magnetic fields, so you'd have to have B to the minus.
Yeah, no, I agree with that.
Be B to the minus n or something, whereas clearly in Plage, B has to be positive. So I think that the Schreiber et al. Approach is probably nonsense. It's a hopeful kind of fishing around in parameter space that you can observe, as opposed to coming at it from a physical point of view from beneath. Energy up equals radiative losses out. Therefore, just the flux is zero. I'm not surprised you can't solve this problem using those parameters.
I see your point, and I agree with it. And then I ask you the question of how else can you parameterize the heating? Give me the model. I'll make a.
Parameterize the heating. I think you should build a physical model from the outset, compare with observations that way.
And how are we going to? How else can we convert the physical model into synthetic observations?
Well, I mean, steps towards that have been taken by the Oslo group.
MHD.
So when you look at it from a parametric point of view, like Schreiber continues to do all the time, you're going to end up with some funny pictures because it's just not physical. You have to come at it from a physical point of view. Energy flux in equals the energy flux out. The radiation only will take care of itself, and that's what I'd like to see. But I think it is very interesting, but it's perhaps misleading to think that you're looking at something fundamental here in the coronal heating problem.
I see your point, and I accept it.
I have a quick question. So the anisotropy or flux tubes is flat or squashed. Does it mean it's more likely that in general to have more reconnections?
I wonder myself. We had a long conversation with PC about it the other day. I don't have an answer, but I would like to know the answer. And I just cannot help but smell that something it ought to affect something like that. Be it reconnection or thermal diffusion or something like that.
That's a gradient.
Precisely. I don't have the theoretical estimates of that, but I would like to get them. Thank you.